Welcome back, everyone. This is going to be a messy question, but one that'll actually show you how we start navigating things within the tensor notation and actually give us a firm understanding of everything that is needed. Because we're going to deal with the magnetic field tensor and much more of the theory later on in the development of physics, this is just a fantastic way to get warmed up to it. All right, so for the statement, we want to work out the remaining 5 parts of the antisymmetric tensor, the antisymmetric transformation rule tensor. Okay. Now remember, antisymmetric means that we simply switch the mu and nu, and we have a negative sign associated with that. Symmetric means that we could switch them and they still be positive. That being said, what we need to know is the Lorentz transformation matrix along the x-axis. Remember, we talked about it earlier in the chapter where lambda is the transformation rule. And we see that we have the 0th component being time, and 1, 2, and 3 being the spatial. So here we have the matrix notation. Now let's go ahead and remind ourselves about the transformation notation, i.e. to be a second rank and all that other stuff. T bar mu nu is equal to lambda mu, capital lambda to the mu and subscript lambda, capital lambda to the nu subscript sigma, where we have T untransformed lambda sigma. Here we're going to have to invoke the Einstein summation rules, stating that if we want mu and nu to come out, we have to sum over lambda and sigma, since that's repeated in the indices here. So let's see how we draw that out and see it in real time. All right, so to start, let's go back to the definitions of what we know for symmetric and antisymmetric second-rank tensors. Here, for an antisymmetric second-rank tensor in 4 dimensions, we only have 6 distinct elements, since we know that T mu nu is equal to negative nu mu, with mu being the row and nu being the column. So using the Einstein summation notation, the only other one of the other parts to this that we have to figure out is what is the T bar of 0, 2, which is in the 0th row in the second column. So to do this, we have to transform over lambda 0 subscript lambda, lambda 2 subscript sigma, T of lambda sigma. That being said, let's just write out everything that we know. So first, we're going to have to sum over all the matching indices of lambda sigma for the transformation matrix and the elements of T. So this goes through 0, 0, 1, 0, 2, 0, 3, 0. Okay, so hold the other constant while you write out all the terms. Similarly here, move the sigma to 1, so you see all the sigmas go to 1, and then you run through little lambda of 0, 1, 2, and 3 again. So you see this is going to be quite cumbersome as we cover all these elements. Okay, so you see that's 4, 8, 12, 16 elements, and that's why we go from 0, 0 to 3, 3, and you see how we're going to need to do this. So in the next page, what we'll show is a way to kind of shortcut it moving forward. So if we read off the Lorentz transformation matrix, we see that terms of this 0, 0 term have a 0 there. Okay, because if we want to go to 0, 2, then we had to plug in everything for that to work. And that being said, this term in particular was 0. And we see if it's 0 here, 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 and here, we get a whole bunch of zeros. Similarly, if we plug in all the zeros for every single one of these 16 components, and we just get rid of them first, then we see what we're left with here, which is the transformation location at 0, 0, and 2, 2, 0, 1, and 2, 2. So adding them together, what we see is that we get a gamma from the first term, a 1 from the 2, 2 term, and then for the 0, 1, we get a negative gamma beta, and a 1 from the 2, 2. Does that make sense? Second row, second column. And then we get a 1, 2 there, and then we see both have a gamma, factor that out, and we see that we're left with T of 0, 2 minus beta 1, 2. Okay? So clearly, this is cumbersome. So let's note the zeros in the particular transformation matrix and only compile the non-zero components. When we do that, we quickly see what the others are. So here we see that the transformation of the coordinate 0, 3. Well, here's a summation notation that we have to worry about. And you see that the first one normally lives on the diagonal of interest. So if we want the third component there, then we're going to have to go through the 3, 3, and 3, 3. Last one was the first transformation was 2, 2, and 2, 2. So that's where we're starting to live now. So with that, we get a gamma 1, and we see that we add this with a negative gamma beta, again, running it through. Here what we're doing is, because we know we're anti-symmetric, we can switch the two variables there, or the two mu nus, switch them, and then we just put a minus sign. So the minus minus gives us a positive, and thus we only had to calculate t bar of 0, 3, and that gives us t of 3, 0 as well, just with the minus sign. So be aware that we can kind of manipulate things like that, and we can push things like this just to make us be able to plug in things that we like in a much quicker way. Similarly, we have t12. So as you see, the trend continues. You got a lambda 22, lambda 22, and then we just calculate through. Again, we're trying to put everything in right order that we need, and I'll just let you read through the rest. Again, you get the 3, 3, 3, 3. So you can kind of start to generalize how these things work. Again, you want 2, 3, so this variable tells us we need a 3, 3 term here. Thankfully, we had 1 there. So now we can transform through. That being said, you can kind of see patterns like this pretty quickly, and they do tend to help. Clearly, they're just patterns and not always a general rule for everything. That being said, as soon as you start working with it, you'll see it too. So yeah, we'll see you at the next one.